Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
Robert, you're laughing already. I didn't even say anything funny.
Yeah, well.
You're easy.
I just as I was hitting to turn us on and turn the music off, I got an itch at the back of my head, so I went,
Oh, you're rubbing and scratching already.
Right,
We're just starting,
right? As we start.
Okay, so welcome to episode number 26, season 2.
Yep.
Today is a very special day in the United States. It's election day.
It's election day.
So did you vote, Robert, already?
I did vote. I voted on my way coming in today.
And I voted early, so we both voted. Yay, we did our civic duty.
That's it. And tomorrow we'll have notices about jury duty.
To refresh those lists, right?
Right.
Now, we do have a live chat that's running, so if you have any comments or questions that you'd like to ask throughout the podcast, feel free to use that feature. Also, disclaimer.
I was about to say, after that opening statement, we should probably read the disclaimer, which is the views and opinions expressed in this show are those of myself and Wayne, not the university or the Department of Physics and Astrophysics or the College of Arts and Sciences.
Or any actions that we may undertake.
Yeah.
Any violence that we may commit to on each other.
Well, I don't think we're going to commit violence.
Only accidentally, Robert. If it happened, it was an accident.
Got it.
I never would do that on purpose.
Accident.
Now, astronomy in the news.
Woo!
So, Voyager is back in the news again. Did you notice that? Did you hear about this, by the way?
I've heard some about it. I've heard it from you. I've heard it from other sources. Their main communication array went out, and they've been using a backup system that hasn't been used for, 47 years?
Yeah, since 1981.
Right.
Now, think of the technology, right? If you turned off something back in 1981 and then you turned it on now, let's say an old computer. What's a computer that was around in 1981?
There was computers then?
1981, I think so.
An
The university
Altair.
certainly would have computers.
Yeah, an Altair or
What's
something
that? When
like
did that Pong set come? Pong.
Oh, yeah, that would have been like 76, 77.
Oh, was that? Okay, so let's say you turn that off and turn that. It would work. I'm sure you can buy them probably on eBay for $1 million now or something, right? Should have kept ours, right?
I mean, that was the height of entertainment, batting a little ball back and forth between two bars.
That was the other one. Was it Space Invaders or Asteroids? So you could shoot them. Yeah. Video games have certainly advanced, kept up with the increase in the technology, right?
Right.
So,
but Voyager can't.
Yes, we can't do anything to Voyager. Well, we can reprogram it.
We can reprogram
but we can't swap hardware.
Right.
And so what happened here is, for some reason, I don't think NASA knows the reason yet, is that their fault protection system was tripped. So that the transmitter, which works on a much higher frequency, therefore greater bandwidth, the X band, as they call it.
For those that don't know, bandwidth is scales as frequency, inverse of frequency. So our scales with frequency, inverse of wavelength. Shorter the wavelength, the more information you can put into it.
Yeah, so it's like a greater pipe if you think of data transfer.
Right.
So with the X-band transmitter going down, NASA didn't realize it, but it actually switched to the S-band transmitter, which is a lower frequency, therefore less information. It's going to be a weaker signal.
Right.
In fact, NASA thought, for example, that they would not be able to hear from it on that frequency. And somebody got the idea, why don't you use the Deep Space Network? And there's been upgrades to the Deep Space Network over time.
Yes.
So to be fair, it's not the same system that was in place when the Voyager 1 and 2 were launched back in 1977.
They probably wouldn't have been able to pick it up at
Back then, probably not. So somebody decided, well, let's look at that other frequency in the S-band and see if we can hear it. And sure enough, they picked it up.
Right.
And so therefore you can communicate with it and try to figure out what happened and hopefully go back to the X-band transmitter in sometime in the future. But it's just amazing. This radio, essentially, transmitter didn't work since 1981 when they turned it off. Or was used, put in place as a backup.
And works fine, apparently.
The vacuum tubes warmed up, the humming noise. Well, it's in the vacuum, you wouldn't hear that.
Yeah.
But if your ear was up against the spacecraft, even in the vacuum, you'd hear the vibration.
The vibration.
Yeah. So you can imagine, all that happening, right?
Yeah.
So it's kind of cool, right? It's one of these, like the Energizer bunnies in some sense, right?
Voyager is definitely the space probe that just keeps on ticking. It doesn't. I mean, sooner or later, it's going to run out of power. But hopefully it'll keep ticking until that day.
Yeah, exactly. And so to get a little bit more details about the Voyager, so the image on the left is the real image of the Voyager 1 spacecraft. It was actually launched second.
Yep.
And I guess in 1977, the reporters were a little bit miffed over that. They wanted the first Voyager spacecraft to be launched called Voyager 1, and the next one, of course, be Voyager 2. But the reverse happened. Voyager 2 was launched first, then Voyager 1. And the reason why NASA did it that way in terms of the naming convention was Voyager 1 was on a faster trajectory to get to Jupiter. So Voyager 1 actually passed Voyager 2 on the way to Jupiter and got there ahead of time. And so that's why they call it Voyager 1.
Right. Well, that makes sense in a weird, twisted sort of way. But, you know, one of them also got gravitational kicks from Jupiter and Saturn, and therefore is going actually much faster.
Both of them flew by Jupiter. Yeah, both of them flew by Jupiter and Saturn.
Okay.
Voyager 1 flew by Titan very close, with a few hundred miles, I remember.
Okay.
And then it went on its way after that, but it was on a path that would not take it to any other planet.
Okay.
So when Voyager 2 came along a little bit later, by then NASA realized that Titan is completely cloud covered. You can't see anything in the optical.
Right.
Unless you might have radar like Cassini mission had later on. It could probe a little better its surface and non-optical filters. But when Voyager 2 flew by, they had the option to put it close to Titan again or further away from Titan, but allow it to continue on to Uranus and then Neptune.
Right.
So in hindsight, of course, which is always 20/20.
Right.
It would have been better to have Voyager 1 and 2 do similar trajectories to both of them go by Uranus and Neptune.
Right.
But that was not the case because of the importance that Titan held. Titan is the largest moon of Saturn.
Right.
It's completely cloud covered. We didn't know it at the time. We knew it had an atmosphere of clouds. In fact, people were speculating that the conditions might be right on the surface of Titan to allow life to form.
Right.
And as soon as you use that word life,
bling, bling, bling,
it catches everybody's attention.
Yeah.
And you want to investigate further. So you can't blame those in the early 1980s to make Voyager 1 fly by Titan at a close range.
Titan, I got to admit, correct me if I'm wrong, but it's the largest moon in the solar system, isn't it?
I think so.
And I think it's big. It's definitely bigger in that case than Mercury.
Mercury, yeah.
So if it were out there orbiting the sun in its own right, it would be a planet.
Well, remember we talked about the Dragonfly mission that was approved and going to be launched here in a few years, where it's actually going to go to Titan and fly around because the atmosphere is thick enough you can do that with a helicopter drone type of instrument.
Just cool. That's
good. And go to
I hope I'm around to see that because that's just going to be so cool.
And remember, it has a sampler on board, so it can sample different places and then chemically analyze the material, the soil, send that information back to Earth. In fact, it's so cold on the surface, that's what goes against the life idea.
Right.
That it's extremely cold. That you have liquids of methane.
Right. Liquid ethane and methane, yeah.
And so you can imagine, like in the future, a spacecraft will go to Titan, a little tube would come out, they suck in a bunch of methane as their power source, and then on it goes.
On it goes. Absolutely.
So you can imagine all kinds of sci-fi type of things happening, right?
I mean, it's great things. I love it. Love to find out new things. And, you know, the reason I asked if it was the largest moon, because that's either Titan or Ganymede.
Yeah, I believe it's Titan, but don't hold me to that.
Yeah. Gany's pretty interesting in its own right for other reasons.
Well, yeah, Ganymede, so that's a satellite of Jupiter. And so the Europa Clipper mission
should look at it.
Yes, because it'll be looking at more than just Europa. Obviously, they're not going to ignore the other moons of Jupiter and Jupiter itself.
Well, I mean, all four of the big moons of Jupiter, the Galilean satellites, are interesting in their own way. Ganymede and Callisto are large, huge moons. Ice, there's evidence that they may hold subterranean, sub-ice oceans as well, like Europa. Europa almost certainly does. Io, volcanically active body. Holy cow.
Well, it's almost as if each planet, like Jupiter and Saturn and Uranus and Neptune with all the moons and stuff, it's like its own miniature solar system.
Right.
And so you can imagine how much time is required to do detailed scientific analysis of all the bodies in the Jovian system or the Saturnian system and so on. I mean, you're going to be there for hundreds of years studying this stuff.
I look forward to it.
Well, I mean, we're studying it now.
But,
right?
Right.
Now, do you remember the first spacecraft to fly by Jupiter?
First one to, wouldn't that be one of the Pioneers? Pioneer
10.
10?
Now, you asked a question earlier, which is the largest moon in the solar system. It's actually Ganymede.
It is Ganymede. Okay.
Yeah, so it has a radius, not a diameter, radius of 1,635 miles.
So that puts it a little bigger than Mercury.
Yeah, so it's bigger than Mercury and Pluto. Well, Pluto, obviously.
Obviously.
You know yeah. But yeah, so that is the largest moon in the solar system.
I knew Ganymede and Callisto were big enough and bright enough that if Jupiter wasn't there to glare, you would actually be able to see them naked eye in the sky at night.
That's exactly right.
So, you know, you don't think of Jupiter, it looks like any other star. You don't think of it casting enough glare, but it casts enough glare that these two naked eye objects can't be seen because of how bright it is.
Now, Titan is a close second. Its radius is about 1,600 miles.
Okay.
So Ganymede is only like 368 miles greater in terms of its radius than Titan. So they're very similar in size.
Right.
So it's easy to get them flipped around. You know.
Like I said, you know, I'm excited. I would love to see missions to both moons because, yeah. But Titan is definitely the more interesting target.
Now, with the Voyager, especially Voyager 1 having been launched back in 1977, you can actually look up on the website. It's a NASA website, and I took a snapshot of it yesterday. That's the panel you see on the right. That can actually tells you updated information. When it was launched, how long ago that was, the distance from the Earth, the distance from the Sun, how fast is it going with respect to the Sun, and the travel time for the radio signal, which would be the speed of light. How long traveling speed of light would it take to get to the spacecraft from Earth, for example?
Right.
So if you look at some of the numbers there, so for example, Voyager, over 47 years ago, it was launched and still going.
And
distance from the Earth, about 166 astronomical units. So what's one astronomical unit is the average distance from the Earth to the Sun.
So it's 166 times.
Times that. It's amazing when you think about it.
Yep.
Distance from the Sun is there, because of course that's not the same as distance from the Earth. It'll change, you know, plus or minus a couple AU at the most, depending on the alignment of everything. But how fast is it going? It's going, you know, nearly 38,000 miles per hour. The spacecraft, and it's slowing down.
Slowing down. You can sit there. I've watched this site before. You can watch it sit there and tick down. It's slowing down.
And some people say, "Oh no, you can't." When you give a force to an object and then stop that force, Newton's law of motion says the object will continue in a straight line at a constant speed. But there's still a force acting on the object.
Right. There's still gravity out there.
Yeah, it's the gravitational force.
The sun's still trying to slow it down and pull it back.
Exactly right. So still slowing down. It's just that it won't slow down enough to return.
Right.
It'll forever be moving away. It's reached escape velocity. And we were talking, you know, off camera, if you like, earlier today, the escape velocity of the solar system at the distance of Pluto, which is 40 AU from the sun, is on the order of 15,000 miles per hour.
Yeah.
This object is a lot further out, so the escape velocity is a lot less, but it's going 38,000 miles per hour. So it's well above the escape velocity of where it is now from the solar system.
And this crazy thing is it'll still take tens of thousands of years to reach the nearest star along its path.
Yeah, and that reason it's not even aimed at a star.
Right.
It's aimed in a random direction. Well, the direction was dictated by the fact that you wanted to fly by the different planets at a certain distance and have a certain path to use the gravity assist mode, but it wasn't aimed at all at a star.
No, it wasn't. But that still gives you some clue as to the size of the universe. Even with that speed, you know, the size of our galaxy, it's tens of thousands of years before it even comes close to another star.
Now, if you look at the one-way light travel time, that's the last line on the right side there.
Yep.
In other words, if you send a signal and you transmit it with your radio telescope, the Deep Space Network, let's say, towards Voyager 1, that signal would take almost 23 hours to reach the spacecraft.
By now, it probably would take 23 hours.
Right? Yeah. And then for it to send a signal, so you send it, you know, hello world signal, you know, message to it, and or say, can you hear me? And it would send a signal back. I read you, right? And you'd have to wait 23 hours for that to come back. So you're like 46 hours by the time you push the return button on your keyboard, right? If you're transmitting at that point, how you'd receive that signal.
That signal back.
It's amazing when you think about it. And that's traveling at the speed of light, where it takes only a little over 8 minutes to get to the sun from the Earth, or a second to get to the moon. Right. And that's how far away these spacecrafts are, both Voyager 1 and 2. It's amazing when you think about it.
It's crazy. I mean, there's no other way to describe it. And, you know, we tend to deal with these distances out of hand in astronomy. But when you stop and think about it, it's really incredible.
I think we got our money's worth on this Voyager program.
Yeah. Kind of like Spirit and Opportunity. We got our money's worth out of those rovers. We're getting our money's worth out of these two probes.
Yeah, for sure.
Only Voyager 1 is still transmitting, though, isn't it?
No, I think they're still in contact with Voyager 2, but one of them is in a lot rougher shape in terms of the instruments that are left working. But I believe they're both in contact with NASA. And one you notice is much further away. The Voyager 1 is the furthest.
Right.
And the distance from the sun, if you look at the Voyager 2, is about 138 AU. Mm-hmm. So Voyager 1 is much further away. So, and if you look at the relative speeds, there's a difference there about 4,000 miles per hour.
So Voyager 1 will be much further away for a much longer period of time.
Yeah, it's traveling faster, and it's furthest one out.
Yeah.
And it's not just these two, right? We have Pioneer 10, which was the first one to fly by Jupiter, as you mentioned.
Right.
Pioneer 11, which flew by Jupiter and Saturn. Mm-hmm. And it got to Saturn actually before Voyager 1. So it stole a little bit of the thunder. But its instruments, like the camera, for example, was of much poorer resolution. Yeah. So the pictures were blurrier. But it kind of whet our appetite for what was coming soon thereafter from the Voyager spacecraft. And then we have the New Horizons probe, which flew by Pluto back in 2015. Yep. And that's on its way out of the solar system. So
in fact, it's much faster than these two, so it will eventually catch them up as far as its distance. It's not moving in the same direction.
Yeah, so it was designed to, I forget how many years in total, on order 5 years or roughly 6 years, 7 years, something like that, from launch to flying by Pluto. So it was put on this very fast trajectory. And restrictions, you had to keep the mass extremely low on the spacecraft.
Right. Well, and that has to do with the fact that they wanted to get it to Pluto in a specific time frame as it started moving away from the sun. Yeah,
so Pluto's on this highly elliptical orbit compared to like the Earth's orbit. And there is times when Pluto's actually closer to the sun than Neptune.
Right.
And that's, how many years is that? It's like a couple decades or a decade at least, something on that order. And the idea that people have was that normally when Pluto is at this furthest point from the sun, right, the aphelion, as we would call, then any kind of gases on the surface is all frozen.
Right.
And when Pluto gets closer to the sun, it actually warms up significantly such that a lot of that gas is evaporated and goes into making an atmosphere, a temporary atmosphere on Pluto. So the idea is to try to get to Pluto at a time when it has maybe this temporary atmosphere. And there was a time period, what would that be, like in the late mid-90s onwards until the like 2020s, 2030s.
Something like that, yeah.
There's some time span where we would expect Pluto would at least have an atmosphere. And in fact, the New Horizons probe, that went through similar thing as what the Europa Clipper did. That is, you go through all these budget issues, right? It's canceled, then it's brought back again, then it's canceled, then it's brought back again. Then you downsize it, right?
So that it's not canceled the third time.
You repropose it and all this horrendous. I don't know how these scientists and engineers do this.
No.
Because I would lose patience, long before it got launched type of thing. But they don't. They stick with it. Sometimes your whole career is on one space probe just because it takes so long to get it finally approved and launch. Right. And then to get to the destination.
Right.
And then you take several years, you got to analyze all the data that you get.
Yep.
So it's basically your whole career.
It's your whole career. I mean, some of them, like the Voyager mission, I think they even had a handoff to a junior member of the team at a certain point.
I know there's been several members, including the head guy, Ed Stone, who passed away recently. A lot of people have passed away since at this point, since the mission started in the late 70s.
Right.
So New Horizons probe, just to finish up that line of thought, that was when finally got to Pluto, there was an atmosphere. It saw the limb haze, So the best way to see an atmosphere on a planet when you're passing by is look at the edge of the planet. It's like looking for prominences on the sun.
Right. And especially looking at it, the sun through it.
Yeah, and when it gets on the other side, looking back towards the sun, you see the backscattering effect. It's like a little bit like seeing the lint when there's a sunbeam, light beam coming in through the curtains during the day or something. You see all that lint in the air.
I got to admit, what I found interesting on that was they found structure to the atmosphere.
Yeah.
It was in layers.
Yeah.
And that was just, holy cow, wow.
Yeah, and there's a lot of neat things they found on Pluto, and that's why a lot of planetary scientists argue, as we talked about last podcast, that it should be called a planet because of the interesting things.
I'll still argue it is. It's still a minor planet.
Yeah, why you call it a planet or not, it's still there. Nature doesn't care what labels we put on it, obviously. So
it's all up to our definitions.
Yeah, exactly.
We make the definitions. We can change them. We can change what's what. So, as somebody I heard once put it, Pluto can either be the least of the major planets, or it can be the biggest, the archetypical of the archetype of the minor
planets. Yeah.
Take your pick.
Now, speaking about radio telescopes.
So
since that's how we essentially communicate with Voyager, this was the largest radio telescope that the United States had. In fact, it was the world's largest until the 500-meter FAST telescope built by China came into operation just a couple of years back. This telescope was built in 1963. There's the dish at Arecibo in Puerto Rico. Diameter 1,000 feet, so about 105 meters. So it's the largest single fixed structure radio telescope at the time, and was so for many decades. Now, one of the things that it could do, of course, is actually transmit, not just receive. So it could transmit a radar and bounce it off of asteroids that come nearby to map out its surface.
Right.
In fact, if you go on Google and look for, Arecibo radar mapping of asteroids, you'll probably see a whole slew of these objects.
Didn't they try that with Venus and got some mixed results too?
Yeah, I mean, we've been bouncing radar off of Venus for decades now.
Right.
And that helps us to estimate very precisely the scale of the solar system.
Okay, right.
That's why you would do that. It'd be very important, of course. Once you put probes there, of course, it's a lot easier, right?
Oh, well, yeah.
So
then you got light travel times.
Yes, exactly. You calculate almost precisely if the time code is buried in the signal from onboard clock on the spacecraft, you know exactly the time it takes since therefore you got the distance. But you could do it this way too, which is like before we send space probes in orbit around Venus and so on. So it was a major workhorse that was in through the beginning of the space age, 63. That's when we're really getting gun-ho and to get manned space exploration going. By then, we're in the Gemini era and then heading into the Apollo era at that time.
Right.
And so it did a lot of work for planetary science, in the solar system work and so on. But, unfortunately, things don't last forever.
Nope. So it should have lasted for longer.
Well, that's what we're going to get to today.
Okay.
So on December the 1st, 2020, the secondary, so we want to go back to the previous slide, and you see the main dish, but on top of that, above the main dish, you see a secondary sort of structure.
Gondola.
Yes, so the radio signal would come in, reflect off the parabolic mirror, and get reflected up to what we call the secondary mirror that you see there. And that object is important because that's how you're going to detect the radio signals that reflect off the surface of the main dish. The cables holding that structure snapped, essentially, quote unquote, and we'll show you what that means in a second. But that whole structure just fell straight down. And so you end up with this mess.
Yep.
Now, in 2020, when this occurred, of course, scientists, especially ones who use this, were devastated.
Right. And justifiably so. I mean, this was, like you said, a workhorse.
The people in charge of this is the National Science Foundation. They were ultimately the ones that provide money to keep this thing running. In fact, they're the ones that supported the maintenance of this antenna. And you could argue the maintenance wasn't really done correctly.
Right.
Because it shouldn't have failed. The cables shouldn't have failed. Now, of course, since this time, supporters of this type of science who like to see the observatory rebuilt have asked NSF to do that. And NSF doesn't have a ton of money. And there's other major projects that they support. They just can't afford to build another one. And the argument is, I don't think you really would anyways from the point of view of technology.
Right.
The highest resolution view that we've gotten now with radio telescopes on Earth has been from the Event Horizon telescope, which is not a single telescope, but multiple telescopes fed together in an array-like system.
Well, you can do interferometry with several radio telescopes and get the resolution power of that you can't build a telescope that size.
Now, the only thing you lose is the light gathering ability because it's such a large area.
Yep.
So you can't see as faint stuff. The other thing, I mean, if you're going for the record, you have to make it larger than the one in China, 500 meters across.
Right.
So what are you going to build? Something that's 1,000 meters, a kilometer across?
Let's do it.
How much money is that going to take?
Oh, who knows?
And and who's willing to give that? Where's Elon Musk's number? Do you have that?
I don't
Robert,
have,
I'm sure your friends
I don't
will,
have that on tap. Maybe somebody out there will do, and we can propose it. But
anyways, NSF is not going to replace the antenna. But the reason, since that happened, nearly 4 years ago now, getting close to the 4-year anniversary, why it's brought up now is because there has been a report that was released, and it's by the National Academy of Sciences, Engineering, and Medicine, and they did basically an engineering report as to why the cables let go and that the radio telescope was destroyed. So this was just released back on October 25th, as you can see there this year. So it's relatively new. But there are some points that I wanted to kind of look at in detail. So you can read the report. It's available online. Anybody can look at it. It's not like it's a big secret or something like that. But the interesting thing, if you go to the next slide, is some key words in here. Number one, the cables are in a socket-like construction or setup.
Right.
And they're coated with zinc.
Mm-hmm.
Now, these cables have slipped in the socket. There's motion of the cable within the socket. It turns out that this, believe it or not, is not unusual. They call it zinc creep. And it happens.
Okay.
It's a well-engineered, documented thing. But it's built into, my understanding is, it's built into the construction that you will have this type of motion within these sockets. And that the motion is not to the extent the cable would fly out of the socket and therefore, quote-unquote, snap.
Except obviously it does.
Actually, it happened. So people were wondering, the engineers, when they were investigating this, what actually is the cause of it. And here's the thing that caught my attention. So I'm going to just read part of what you see here at the top. It says, the committee says that the uniquely powerful electromagnetic radiation environment at the telescope likely accelerated the deformation of the zinc, but was unable to prove this definitively. So they're saying that possibly because of the weak EM environment that it's located in, the signals being transmitted and received, that somehow aided the deformation, the failure that happened with these cables.
Go ahead.
Yeah, so that's the idea, that if it would have been in a different type of structure, like a bridge,
it would have been fine.
It would have been fine. But where it was in this type of situation, that added to the failure happening on a shorter time scale than what was predicted.
And I have questions on that. I would like to see some testing done on that because, radio waves are non-ionizing. They don't pack a lot of punch. Granted, you are concentrating a lot of it and therefore a lot of overall power, but you're not knocking around the electrons really or anything like that.
Well, come on, Robert. Can't you detect radio signals? Can't you listen to the nearby AM station on your braces in your mouth?
I'm not going to go there. I know there are claims that you can, but I've not heard of any credible testing of such.
So what does EM waves actually do over a long period of time since the early 60s when you're transmitting probably at high power to radar signals that bounce off these asteroids? What does that really do to the metallic structure?
And that's why I'm saying I would like to see a study done on it, but I don't know that I'm necessarily buying it without that. Call me the doubter, but,
Debbie Doubter.
That's me. Sorry.
But the other thing here is kind of interesting is that there was a corrosion issue, and NSF knew about it as far as I know, and yet didn't. Yeah. They were planning to do something about it. They just didn't get onto it fast enough. Now, maybe it was a cost-saving issue. I don't know.
Now, that's something I could see, the high-power radio waves doing is causing corrosion to happen faster because you are energizing the electrons in that metal. You're making them move faster. So I could see that being a problem with corrosion and that leading to failure.
Well, put it this way, you wouldn't want to stand on the edge of this dish when it's transmitting if you plan to have children. You know?
Not if you're planning on having children. But again, it's not because it's ionizing and breaking down the molecular bonds. It's because you're cooking.
Yeah. It's not a good place to be.
It's not a good place to be.
So one would think it might have some effect on metals.
I can buy it. Don't get me wrong. I can buy it. I'd just like to see some testing of that idea done.
Notice they said that they couldn't prove it.
Right.
Definitively prove it.
Yeah.
So, I mean, what testing can you do? You can do very short-term testing. You could stick this type of metal near a transmitter and look at the structure and then look at the strength of it afterwards, right, and test it. But how long does it have to, if it needs to be exposed for decades, then you don't have that time to wait around.
Then you don't, but you can also do things like ramping up the power that it receives.
Well, what about looking at similar structure,
look at similar
from other radio telescopes that are still being operated? Can't we see any, do any tests on them, any degradation,
a good question
right?
too. Yeah. Because this zinc coating thing is a common thing for dealing with weathering and corrosion.
Yeah. I mean, that's why you can go to a hardware store or whatever, your favorite box store.
Nails.
Yeah, and zinc coated plated stuff that you can use outside and stuff. So it makes sense in that sense.
It does make sense. And it should be something easy enough to follow up on and say, yep, this is a problem. Because as we're saying, it is something that's ubiquitous in the world of construction, especially things that are outside.
And the image that you see on the bottom, that's after it collapsed. So you can see the devastation. It's a shame, really, when you think about it. There was still use for this telescope.
Right.
And compare it to the cost of replacing it, to what it would have cost to do the maintenance work.
Yeah.
I mean, we probably should have been a little bit smarter on that and kept it going.
I'm not a radio astronomer, and I was sad the day that this happened. Yeah.
Well,
there was a lot of good work being done.
And later on today, we're going to talk about an asteroid that's going to fly by close to us in 2029. It would be nice to have this available, the Arecibo dish, to bounce radar off of it.
Absolutely.
To get good mapping of it.
Yeah.
Or anything else, right? There can be some unknown that we don't know that even exists today that bypasses us in a decade or so.
Right.
And that we want to do detailed study with. And there's no spacecraft in space at the time and place to be able to get close up to the object. Then what are you going to do? Well, one way is to bounce radar off it, so we use it as the transmitter for that.
Yep.
In fact, a lot of the science then is you look at pulsars.
Mm-hmm.
And then, so pulsar study, if you want to just continue on the thought.
Oh, okay. Sorry.
Just so we're not
Sorry,
rushing.
folks.
We're not, we have enough time to go into it a little bit detail here.
Yeah.
But one of the major studies that was done with the Arecibo is to look for pulsars.
Right.
And if you want to understand the evolution of massive stars, so you want to describe what a pulsar is, Robert?
Well, it's a neutron star, so it's a massive star that collapses. It doesn't have enough mass to collapse down to a black hole. We don't know quite what that mass limit is. So it leaves behind this cinder where all the electrons have been driven into the nuclei. They combine through some processes we won't get into with the protons. They form neutrons, hence the name neutron star. It's essentially a planet-sized, I think.
Oh, neutron stars would be city-sized
object with the mass of several of our suns, a couple of our suns. And it's essentially a giant atomic nuclei. That said, the magnetic fields are conserved and all that, so they strengthen. So this pulsar is one of these neutron stars with beams of radio waves and other light electromagnetic radiation going out from its magnetic poles. And if we're in the way, it's got this lighthouse effect if one of those beams sweeps in our direction. And so we catch it, and it was originally found and thought to be an alien signal, as a matter of fact.
Do you remember who found it first?
Bell?
Yes.
Yeah. Caitlin?
No, Jocelyn.
Jocelyn Bell.
In fact, I heard a presentation that she made a couple of years back, and where she used a good analogy to describe how bizarre the environment of a neutron star is, because of so much mass compressed into such a tiny volume of space. If you could, and you can't, but if you could stand on the surface of a neutron star and you held out a baseball in your arm, horizontal with respect to the surface at your height, and you drop the baseball, so starting from rest, by the time the baseball hits the surface of the neutron star, it's traveling half the speed of light.
Yep. It's crazy. It's some ridiculous environments out there.
And in the news today, I noticed they discovered a pulsar that spins over 700 times in 1 second.
In 1 second.
So that's the fastest rotating pulsar neutron star that they've ever discovered.
Sorry, folks. That also is another thing that's conserved is the angular momentum, the rotation rate. So think of it as a skater drawing in their arms. So we start out with a big star, several times the radius of our sun, spinning probably fairly slowly, but that's not necessarily true either. And as they draw in the arms, as it collapses down to a city-sized ball, it spins that much faster and faster and faster until it's spinning once every, 700th of a second.
So this particular one, which was announced today, it goes around 716 times in 1 second.
Right.
So it only takes 1/716th
of a
second to go around once.
These are what we call the microsecond pulsars.
Yeah, these are very, very, very fast spinning.
Yep.
In fact, there should be a limit. You go so fast. Of course, they're really dense, so they can hang on to themselves. But there's going to be some limit where the thing would just fly apart
again.
If it's traveling any faster.
Right.
But that whole thing you said about your arms outstretched and you bring them in and you spin faster, in physics we call that the conservation of
angular momentum.
Of angular momentum.
Yep.
So that's the only analogy I heard about the conservation of angular momentum that's popular.
Is usually the ice skater.
It's the ice skater one.
Yep.
So we should think of something else to get tired of.
We should. Because there's plenty of other things that rotate out there.
Yeah, so. And you just have something that extends its size and then it changes its rotation. Either become larger, slows down, or get more compact and speeds up.
Spins up.
So, I mean, you can do demonstrations, but I mean something to say by words where people... And you got to pick something that people have seen. You can't some obscure centrifuge device that you have. I don't know what's that, right? You can't use that. So if you take a person and you grab them by the ankles and whip them around your head,
and now let them curl into a ball.
Assume you don't let go. So you got to be non-violent examples, right?
Right.
So maybe we just stick with the figure skater.
For now.
Safe that way.
All right. So now where did this?
So the other thing that I noticed is in the news lately is this issue once again related to, well, there's more than one company, but let's pick on SpaceX. I'm not picking on them any personal type of vendetta or whatever, or anything to do with politics. It's just that they're the ones that are really advancing in this field, and this is to launch all of these satellites, especially for the Starlink program.
The Starlinks.
To give you another option of getting your internet, especially if you're in the middle of nowhere, essentially, right? So satellite internet. The problem is if the satellites are in a really high geostationary orbit, there's a latency effect. It turns out by going through the ground station and then up to the satellite and back again and back through the ground station to get processed and all of this stuff. There's actually a delay where if you hit the keyboard, it takes a significant amount of time for the thing to show up on your
amount of time.
Yeah, to show up on another computer that you're communicating with. And people don't like that, of course. They want that instantaneously if they can do it.
Right.
Of course, you're restricted by light speed. So the idea was, well, put the satellites in low Earth orbit, several hundred miles, 500-600 miles up or whatever. And then the signals can bounce a lot faster, the travel time from the Earth's surface to the satellites and back again. And that would decrease that latency. So then you have an advantage over who's some of the Hughes satellite company or whatever.
Something like that.
They have their own satellite internet, and so but they got the latency problem because they're in much higher orbit. But Starlink, the relatively new internet satellite system that you can purchase then, is a lot better in that sense. The latency is a lot smaller, so you can you can handle the little bit of delay that would be there. It's not that bad. But that means putting up, because they're not in geostationary orbit, technically you need, 3 satellites minimum to cover the surface of the Earth?
Right.
4 or 5 would be better, but 3 minimum.
Right. 3 minimum.
But where these are not in geostationary orbit just means that you're rotating at the same rate as the Earth below you.
Right.
So you maintain, relative to the Earth below, the same location.
Yeah, I remember as a kid, that was the main weather satellites were in geosynchronous orbit.
In fact, that area, it's a curve, right, that goes around the Earth. That is populated by satellites now.
Right.
There's a lot of satellites up there in geostationary orbit, and they got it situated where if one of them starts to get old and they want to retire, they can move it out of that orbit so they can open up a spot for another satellite to move in there.
Yep.
So that's very valuable real estate.
Very costly to get it there, too, though.
Well, that's it. And if anything goes wrong, how do you repeer it?
Well,
that's the other issue, right?
Yeah.
It's very difficult.
You're not sending up a space shuttle.
No, and so to get around all of that, to utilize low Earth orbit, you got to have at any given time several satellites above you.
Right.
It's like the GPS system where you need at least 3 for triangulation.
Right.
So you're going to have. So that means that you're going to have to put up literally tens of thousands of satellites. In fact, if you look at the different companies, not just SpaceX, like OneWeb is another one. I think Europeans have one. Probably Russia is having this, thinking about it. China and all these other countries too. And so, you're looking at up to 500,000 of these low Earth orbit satellites that are going to be put up over the next several years. And there's thousands of them up already. Every couple of days, it seems like there's a SpaceX launch putting up these satellites.
What's the problems with low Earth orbit, though?
So in low Earth orbit, you're essentially still in Earth's atmosphere.
Right.
And the atmosphere of Earth is not like a cutoff, right? You get above 50 miles and then there's no atmosphere. It doesn't work that way. It's a gas, so it's diffuse. It's not well defined. Anytime there's a lot of solar activity going on, like nowadays where the sun is going through its solar maximum, that energizes the Earth's atmosphere, so it actually puffs out further. Times when there's less solar activity, it can contract downwards a bit. So the actual boundary, however you want to define the atmosphere, actually can change dramatically.
Right.
And so a lot of times these satellites, like Skylab, got caught in the 70s.
Skylab got caught in it. Yeah.
The ultimate plan was to take the space shuttle on one of its early flights,
and
which was supposed to be launched in the late 1970s, to have a rocket that would hook on the Skylab and boost it into a higher orbit to preserve it, to be able to use it later. Mm-hmm. But before the space shuttle was even launched, which was in 81, Skylab came down like in the late 70s. Yep. And that's because the atmosphere had puffed out a bit because of the solar activity and brought it down a little faster than what they had thought would happen.
Right.
So the same thing can happen to these satellites. And so you need lots of these satellites up there, and some of them are re-entering there. Right? They're not on these long-term stable orbits. And what are the satellites made of? Well, they're made of a lot of aluminum.
A lot of aluminum, some magnesium, manganese, iridium, platinum, gold.
And so when these satellites come back, you're burning up the aluminum with the oxygen environment, and you're forming lots of aluminum oxide, which is not good. In fact, what you're seeing here on this slide is a letter that's signed by a number of astronomers and scientists that's addressed to the FCC, so the Federal Communications Commission. And basically what they want, and you look at the first line of it. Here's the first sentence, which is kind of interesting. We should look before we leap, period. That's the first sentence. And you're like, what? Okay, what's this all about? And they're making an argument that we need to look carefully at the approval of all these satellites that are being launched from U.S.-based companies, like SpaceX, for example, that we should look at how many are going to be put up there in the next several years, right? And there's going to be more and more all the time. In fact, they're talking about, 58,000 will be launched by 2030, and then maybe 500,000, over the whole lifetime of this satellite internet. And there are a couple of issues. The one for astronomers, of course, on the ground is the problem that these satellites are moving across all the time, wherever you look in the sky, and you're going to get these long, nasty streaks in whatever images you're going to capture.
Right.
And in fact, the LSST, so the Rubin Observatory, which is an 8-meter class telescope in Chile, is soon going to be operating, doing the LSST, which is this large-scale view of the southern sky. Every 3 nights is going to cover the southern sky. Well, during those exposures, since they're looking at a huge area of the sky,
there's going to be several satellites going.
There's going to be tracks going across all the time, essentially.
Yep.
In fact, you can actually see these satellites yourself. You don't need anything else. Just go out at night after it gets dark and look up in the sky, and you'll see these satellites moving. There's a huge number of them. Or look just before it gets daylight, and you can see them. Because then the alignment is usually best for reflection of the light off the satellites.
I caught them in airplanes all the time when I was doing astroimaging a decade or two ago.
Yeah, so I mean, there's lots of them up there, and it's only going to get more and more and more.
It's going to get worse.
So there's an issue with astronomers. Now, of course, people run the Elon Musk and SpaceX and complain, and he said, well, put your telescopes in space, but that costs a lot.
You pay for it.
Yeah, that costs a lot of money. It's way cheaper to be on the ground to do these kind of things for expense-wise. And the other thing that the argument here is not only does it will mess up, the viewing of the night sky, especially telescopes, and these telescopes like the Vera Rubin, I mean, they're these, large, like even 30-meter telescope that's planned. You're talking $1 billion. $1
billion.
So you're investing $1 billion in these projects, and yet you got to put up with the degradation caused by all these trails going across your images.
Right.
Now, there are ways to compensate for it. It's not like it's total loss, but it just makes it tougher. The analysis is more substantial. But so that really, if you make that argument to the government, not a lot of people are going to care.
Yeah.
They're like, suck it up, buttercup, and deal with it.
We've been making that same argument for a long time about light pollution from street lights, and look where it's gotten us.
Yeah, if you want to hear about that, by the way, go to season 1, episode 1.
Absolutely.
We went right into the whole aspect of light pollution. And so what scientists have done, astronomers in particular now, have added to the argument.
Right.
Now, and it's kind of smart when you think about it.
It's a good argument.
So here's the argument, right? That you got to put up so many of these satellites, and because they're in low Earth orbit, a large number of them per year are going to decay. And that's going to burn up. And all that material is going to go into the atmosphere to cause pollution. Now, how much are we talking about? Well, by the time we get all these satellites up, you're looking at, listen to this, 29 tons per day of material that's going to be added to our upper atmosphere. Pollution, the aluminum oxide. And that will cause?
Cancer.
Climate change.
Oh, that too.
Climate change.
When it filters down to the surface.
Boy, if you want to do a study and if you want to get it supported by the federal government, use the words climate change. Right now, the environment is such, no pun intended, that the federal dollars are available if you do anything related to climate change. Now, I'm not arguing that this is not a fact or not. I'm just saying that to get people's attention on this issue, if you can invoke like climate change, you're going to go a lot further just saying it's going to ruin my pretty astronomy images that I'm going to take with my camera and my telescope.
Right.
Because nobody's going to care about that.
Because nobody cares about that.
Who matter.
Right.
So this is a major, I never even thought about this before, what impact this would have on our climate by having so many of these satellites burning up in the upper atmosphere.
Yeah, what is it that aluminum oxide would probably be, I don't know what it would do.
Who knows? I mean, atmospheric science is very complicated.
But 29 tons a day is a lot.
It'd be interesting to have somebody on here, a guest who's an atmospheric scientist that would actually describe in detail what is the impact of 29 tons per day of aluminum oxide dumped into our upper atmosphere.
Yeah.
Anytime you're putting stuff in our atmosphere that shouldn't really be there, it's probably going to be a negative effect.
It's probably not going to be a fun effect. Yeah.
Anyway, so we'll see what happens. But you got what big business can you say? Big corporation, big powerful people with lots of money
who want to put these satellites
against what? It's not the average, but against the science, I guess you would say, against scientists. So it'll be interesting to see how this all plays out. And today is election day, and I wouldn't doubt that depending on the outcome of this election would actually tell us what's going to happen with this type of letter. Right. How it's received at the federal government level will depend on which party is in power.
Yes. And that's a shame because it should be a concern for everybody.
Well, it'd be nice if people actually did scientific study and see what the real impact is.
Right.
Don't go by what you think it is. Right?
Right.
Actually do the work and see what the numbers tell you.
I agree.
But anyways. So the other interesting thing was in the news recently. So there's this about satellite pollution. Yeah. This just kind of illustrates the point here. So there's an image from SpaceX showing the Starlink satellites Like I said, I'm not picking on them, but they're the most successful company at the moment.
Right.
So the vast majority of those satellites in low Earth orbit are from SpaceX.
From Starlink and SpaceX.
Right. And just to illustrate the point that, when they do, and they can't stay up there forever. When they do come in, they'll burn up, and all that material will add to the pollution of the upper atmosphere. There's no doubt about it.
No.
So even if we stopped it right now, the ones that are up there
are still going to
still have to burn up in
the
the atmosphere and add junk to it. I mean, you have no. I mean, people even argued about the space shuttle. We shouldn't be launching that. Right. It's not because of the main engines, because that was hydrogen and oxygen. So the byproduct of combustion is water.
Water.
So that's not going to damage anything. It was the aluminum perchlorate or chloride that was in the solid propellant and the solid rocket boosters.
Okay.
That causes major pollution.
Yes.
And so that you can make an argument, hey, we shouldn't be launching these things like every week or every 2 weeks like NASA initially planned, because that will contribute to climate change.
Right. And just general pollution.
Yeah, but we ended up not launching as many as we had thought. Like, I don't know it'd be nice to figure out what the average launch was, the time between launches. Yeah. Probably every so many, like 4 or 5 months or something on like average. It wasn't that good. We tried to speed that up and we got us in trouble. Yeah. Right? It bit us. We ended up losing a couple vehicles by doing that. But anyways, so moving on. So the other thing that was interesting in the news is that European Space Agency has officially approved a mission called the Rapid Apophis Mission for Space Safety. So you see the acronym there? What is it?
Ramesses.
So this mission is designed to actually go and look at the asteroid Apophis. Now, the image that you see of Apophis is not a real image.
Nope.
We haven't flown any spacecraft by it. This is just an artist's impression, what an artist think it might look like, right? Based on what we know that asteroids do look like.
I was about to say, I think the shape is pretty much right, because we've done all kinds of light curve studies on it.
Yeah, and it's probably not going to be looking like a hockey puck. We can narrow it down a little better than that. Or it's not going to be a Big Mac in space flying. Woohoo! Right? Because we've flown by other asteroids and had close-up images, so we know what they are or what they look like roughly. But the interesting thing about this asteroid is that it will fly by the Earth in April of 2029 at a fairly close distance, 20,000 miles.
Wow.
Right? Now, the diameter of this sucker is 350 meters.
That's a city killer.
If this were to impact the Earth, major damage. Especially if you, like you said, if it hit a metropolitan area.
That's a city killer.
Game over.
Yeah.
For anybody who's in that city. Now, this is the asteroid that people have talked about a lot. That when it does fly by in 2029, if it flies by at the right trajectory, or maybe the wrong trajectory.
Right time, the right place.
Yeah. It could possibly set up an additional flyby later on, I forget how many years later, but several years later, where it actually could impact the Earth. That was the scare.
Right.
That's the scare. Now, I don't know if that's 100% gone away with better data, but there are these keyhole trajectories that these objects can be on. If it hits the keyhole, then it lines itself up for an impact with the Earth in, a couple decades or something, or whatever it is.
I mean, it'll do another flyby. I think it's in 2045. They're pretty confident now that it's going to miss the keyhole in 2029.
Pretty confident?
Yeah. I mean, it's never a 0% chance.
Yes. So it's non-zero chance. It's fair to say.
It's very tiny, but it's non-zero.
But it's very low.
Yes.
Yeah. So since it's coming very close, in fact, it's large enough that it should be visible to the unaided eye at its closest approach.
Probably look like a satellite just streaking across the sky. Yeah.
So what the European Space Agency is doing is they're going to have a spacecraft out there to actually make a close approach in February, so 2 months before it flies by the Earth, of 2029, to get detailed analysis of the object itself, just on the off chance not only that this object may be on a collision course in the future, but you never know, some other asteroid maybe at such a path in the future that would ultimately hit the Earth. And we want to find everything we can about asteroids, because that will help us determine what type of mitigation system we need. Do you want to send nuclear weapons, for example, to blow this thing up? Or do you can you hit it with a projectile to alter its course if you hit it early enough so it doesn't, hit the Earth?
Do you want to send the nuke but blow it up off to the side a little bit and do a standoff blast.
You had to give it a little bit of a push in some different direction, an impulse to get it off the path that it's on, the collision course path.
Right.
So there's a whole bunch of things we can think of. Most of those things have to be done early.
Got to have time.
So the key is finding these guys that are going to be heading towards us. In fact, Congress had mandated that, I believe it was NASA, or at least astronomers, would be able to find, all of the asteroids that could potentially impact the Earth above a certain size.
Right.
And a lot of that work was done like with the WISE spacecraft of NASA, the infrared spacecraft, to look for these things.
And if you want a list of them that are coming close in the near, in a rough time frame around where you are right now, spaceweather.com keeps track of the near-Earth asteroids that are in the area. So if you're interested in such things, check them out. You also get a lot of information about space weather, what the sun's doing, and so forth.
Yeah, so Apophis will make this close approach in 2029, and the other one will be in 2036.
2036.
And it's not expected to hit us. In fact, they say it's not going to hit us for at least 100 years.
There you go.
So, Robert, you and I won't have to worry about it.
Hey, speak for yourself.
But others will. And hopefully the technology have advanced to a point where even if it ends up being an object like this, if not Apophis itself, that we are able to deal with it.
Right. I mean, this is a natural disaster we do have the capability of dealing with.
And that's the argument for not getting rid of our space program.
Absolutely.
I mean, we do need one, even if it's, it could save the world.
Yeah.
So then the investment.
Apophis, nature's way of asking, how's that space program coming?
Yeah, well, you might complain, we've put in several $100 billion over the lifetime of the space program or whatever the number is. Yeah, but how much money does the world cost?
Right. There you go.
If you destroy it completely because of a large asteroid that hits us. And right now, if they're above a certain mass, of course, we can't do anything.
Right.
So, what do you do? One idea is an interesting one is you put a massive object nearby so the gravitational interaction pulls the asteroid off its course. But once again, you have to have several years advance notice.
Right.
So
another one I've heard that does a similar thing is to take one of these massive solar sails that they've now proven the technology of and attaching it to the asteroid so that it gets that little tug, that little push off of its orbit, because it just takes a small tug and it will miss us.
Yeah. So that's why it's so important to have, some group of scientists that are looking for these things all the time, because we need that advance warning in order to improve our odds of doing the right thing.
That's it.
So it's kind of cool when you think about it. But if you want to be part of that, if you want to be in a team that helps design how to get rid of these asteroids, to knock them off course, one way to do that, of course, is to get
a degree in physics or astronomy or astrophysics
or engineering
or aerospace studies, or, maybe you want to talk to Congress critters about this stuff. And so you need political science or English degree.
Exactly. So higher education is the key here. And so one of the places you can come here, of course, is the University of North Dakota here in Grand Forks. And we do have online as well as on-campus programs. So there are lots of exciting things happening and lots of things to choose from. So hopefully you will find something that fits into your interests.
That's the plan. And you should try it. And if you come by campus, come see us.
The other thing that we never really say a lot about is it's actually quite affordable here at the University of North Dakota.
Absolutely.
You don't need to mortgage your future to come here.
Absolutely.
So
you might feel like it, but you don't.
Take advantage of it. I mean, I can think of other places which I won't name that are a lot more expensive than the University of North Dakota when it comes to tuition.
Yes.
And everything else, the fees and all that stuff piled in there.
Right.
So, in those places, you do mortgage the future, it seems like. But anyways, that's it for today. Now, we will be back on next Tuesday, November the 12th. The other thing is we always leave you with a quote. So today's quote, fittingly, is by Carl Sagan.
Okay.
So here's the quote. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. Please give us a thumbs up. Subscribe if you haven't already, and we'll see you next time. Thank you.
See you next time, folks.